Have you ever wondered what matter really is beyond the solid, liquid, and gas we meet every day? Imagine a world where atoms move like a single wave, or where they freeze not from cold, but from quantum precision. In labs across the planet, scientists have coaxed matter into strange, exotic states. Plasmas hotter than the sun, condensates colder than space itself, and materials that defy the rules written in every textbook you've ever seen. Each one reveals a hidden version of reality, built from the same particles, obeying the same laws, but behaving in ways that seem impossible. If that kind of quiet curiosity feels like home, a light tap on like and subscribe helps others find this journey too. Settle in, and let's explore how matter becomes truly strange. What is a solid? It sounds simple. A solid keeps its shape. It doesn't flow, and it doesn't squash unless you push hard. A rock, a chair, a spoon. That picture works for daily life. Yet even this basic idea starts to blur when you look closer. School teaches 3 states: solid, liquid, gas. Solids hold shape and volume. Their atoms sit in a regular pattern called a lattice. They can vibrate, but don't trade places. Liquids keep a steady volume, but take the shape of their container. Their particles stay close, yet slide around one another, so they flow. Gases spread out and fill any space. Their particles are far apart and move freely. That little chart is useful. Ice is solid, water is liquid, steam is gas. It explains cooking, weather, and simple experiments. But nature is broader than a classroom diagram. Even inside the group we call solids, order is not guaranteed. Some materials like glass and obsidian are amorphous. Amorphous means there's no long-range pattern in how atoms line up. At the atomic scale, these materials look like a liquid that has been stopped in place, crowded, and disordered, but stiff. They behave as solids at room temperature, yet their lack of a repeating structure gives them unusual traits. They can look clear, break in sharp edges, and show different responses to heat and stress compared with crystals such as salt or quartz. So solid is often a description of behavior, how a substance responds to forces, more than a strict category with clean walls. Time also matters. Pitch, a tar-like material, seems solid if you tap it. Leave it alone long enough, and it flows. That flow is incredibly slow, but it exists. The idea is uncomfortable because it asks us to judge matter not just by what it is, but by how fast it changes. Wait long enough, and a solid can creep. The borders between other states blur too. The line between liquid and gas vanishes at high temperature and pressure. Past a certain point, a substance becomes supercritical. It can move through space like a gas while dissolving things like a liquid. Carbon dioxide is a common example in industry. Supercritical CO2 can extract flavors and oils without using traditional solvents. In that region of the phase diagram, our tidy labels don't separate neatly. Properties blend in a continuous way. If you push conditions further, much colder, much hotter, far denser, or under strong fields, new phases show up. Plasmas are one of them. A plasma is a gas where atoms have been stripped of some electrons, so you get a mix of ions and free electrons. It conducts electricity and responds strongly to magnetic fields. Plasmas glow in neon signs and fluorescent lamps, flash in lightning, and dominate the Sunday. People sometimes call plasma the fourth state, But there are many more states if you count how structure and motion can organize. Many materials reveal surprises under pressure or in strong magnetic or electric fields. Some rearrange their internal pattern, others change how they conduct heat or carry electric current. These changes are not random. They follow rules set by how particles interact and how much energy is in the system. Temperature and pressure are the main tools we use to move from one region to another. Add heat, remove heat, compress or release, and a substance may switch phase. In quantum systems, or in extremes, those rules can bend into behaviors that are not obvious from everyday experience. It helps to focus on phase transitions, the turning points, melting, freezing, boiling, condensing. These are times when structure changes and properties switch. At a transition, small motions add up. Bonds break or form. Vibrations change. What was brittle can become slippery. What was fluid can settle into a pattern. You see a small version of this when your breath fogs on a cold morning. Invisible water vapor becomes tiny liquid droplets and then fades again as they evaporate. A familiar puff, yet it marks a real change in state. The common three states are the surface layer of a wider map. Below that surface lies a landscape of order and disorder, stability and slow drift. Nature only has to be consistent, not simple. Our categories help us navigate, but they are tools, not borders. This brings us back to solids and to a famous story about glass. People sometimes say that old windows are thicker at the bottom because glass flowed over centuries. The story is neat, and it feels like it respects slow time, but it confuses how glass is made with how it behaves at room temperature. Glass is an amorphous solid. Unlike a crystal, it does not have a repeating pattern over long distances. If you could zoom in on quartz, you would see a tidy three-dimensional grid, the same motif repeated again and again. In glass, the atoms are arranged in a disordered network. They are locked together. They vibrate in place, but they do not line up into a crystal pattern. Think of a crowd that has stopped moving. People are close. They are not trading places, yet they never formed rows. That lack of long-range order explains several traits. Glass can be transparent across a broad range of wavelengths. It can shatter into irregular pieces. It softens smoothly with heat instead of melting at a sharp, single temperature, like many crystals. These are signs of structure, not of slow flowing under normal conditions. Why are old panes uneven then? Historical method. Before modern float glass production, makers used crown and cylinder techniques. In the crown method, a glass blower spun a disc of molten glass and later cut panes from it. In the cylinder method, a long tube was blown, slit, reheated, and flattened. Both methods produced sheets with variable thickness. When installed, glaziers often put the heavier side down for stability. Careful surveys of antique windows show that the thicker edge can be at the bottom, the top, or the side. If gravity-driven flow at room temperature were the cause, the thicker edge would always be at the bottom. It is not. There is also the question of rate. To see a measurable sag in window glass at room temperature would require a timescale longer than human history by a wide margin. The viscosity, the measure of resistance to flow, is so high that, for practical purposes, glass does not flow at ambient conditions. Yet the myth persists because there is a grain of truth, and that truth lives at high temperature. When glass is formed, it behaves like a very viscous liquid. At thousands of degrees, it can be gathered, blown, stretched, and molded. As it cools, its molecules move less. Instead of a sudden freeze, motion slows until, effectively, it stops. The solid you get is glassy, stiff, but still lacking the repeating pattern of a crystal. This slow settling into rigidity is called the glass transition. A transition is a change, but this one is not a sharp on-off switch. In many crystalline materials, melting or freezing happens at a clear temperature. Cross that line and structure changes abruptly. In glass-forming materials, the change is spread out. As you lower the temperature, molecular motion becomes sluggish, then so slow that, on human timescales, it is as if the structure has locked. There is no single instant where it snaps into order. It is a gradual fall into stillness. Because the glass transition is gradual, different cooling histories produce different internal states. Two pieces of the same composition can differ in internal stress, toughness, and optical quality depending on how they were cooled and annealed. This is why careful heat treatment matters in making lenses, screens, and high-strength glass. The pitch story sits next to the glass story but shows a different point. Pitch looks solid. Strike it, and it can shatter. Leave it be, and it will eventually drip. The key is viscosity again. Pitch at room temperature has an enormous viscosity, much higher than water, oil, or even honey at ordinary conditions, yet not infinite. Under its own weight, over many years, it deforms and flows. A long-running test made this clear in a way anyone can understand. At the University of Queensland, a sample of pitch was poured into a funnel and left to settle. Once the material relaxed, the stem was opened and the weighting began. A drop forms and detaches only after many years. The experiment began in 1927 and has produced drops at intervals on the order of years on a human calendar, rather than minutes or days. It takes years for a single drop to form and fall. Despite appearances, pitch is flowing just at a rate so slow that human time can barely register it. This kind of near-frozen flow is not unique to pitch or to glass. Many plastics creep under steady load. Even metals do, if the stress is high enough or the temperature is right. Think of a hot turbine blade that slowly deforms after many hours of use. These materials don't fit neatly in our old boxes. They blur the line between fluid and solid and remind us that a state of matter often depends on timescale. Over seconds, something looks rigid. Over years, it can move. Obsidian belongs to the same broad family of amorphous materials. It forms when lava cools so fast that atoms don't have time to form crystals. The result is a glossy black volcanic glass with a conchoidal fracture, smooth, curved surfaces that break into razor edges. It feels solid because it is solid at room conditions, yet its internal order never fully formed. Nature can skip the crystal step when the cooling clock runs fast. These cases challenge our instincts. We judge with touch and sight. If something clinks when tapped or shatters when dropped, we label it solid. At the atomic scale, those tests are not the rules. Atoms follow energy and motion. They arrange in patterns when they can, and they lock into disorder when cooling traps them. When the rules land between a crystal and a liquid, we get an amorphous solid, neither, and a bit of both. There is a quiet elegance in that in-between state. It is stillness that is not completely still, structure that never quite finished organizing. A window pane with tiny internal stress, a shard of obsidian with a smooth break, a pitch that drips once in many years. All of them show that matter is not in a hurry to pick a perfect label. Calling glass a stubborn liquid misses the point. A better view is to see it as its own kind of order, not a failure to crystallize, but a network that accepts disorder as part of its nature. In a world that loves sharp borders, glass offers a softer boundary and teaches that some materials slip between the lines without losing their identity. Ask people to list the states of matter, and you often hear the classic three. Someone might add plasma, like a late guest. Yet plasma is not rare at all. It is the most common state in the visible universe. It is scarce at Earth's surface, but the cosmos runs on it. Stars are hot plasma spheres. The sun, bright nebulae, and much of the thin gas between stars and galaxies are plasma. Even the curtains of the northern and southern lights are shaped by it. Plasma is an ionized gas. Add enough energy by heating or with electric fields, and some electrons break free from their atoms. The gas is no longer a collection of neutral atoms. It becomes a mix of positively charged ions and free electrons that move and interact together. That change unlocks new behavior. The material conducts electricity well. It makes and responds to magnetic fields. It supports waves, filaments, and sudden bursts that can travel and twist over long distances. We do not meet plasma often in daily life, but it is here. Lightning is a short, bright channel of plasma. Flames can have a small plasma component at high temperature. Neon signs and fluorescent lights use low-pressure gases energized by electricity. The glow you see is the light from atoms and ions, as electrons drop to lower energy levels. Some welding tools rely on a focused plasma jet to melt and cut metal. What makes plasma feel so different is its sensitivity to electromagnetic forces. A neutral gas drifts and mixes. A plasma can be guided, confined, or shaped by electric and magnetic fields. Engineers use this fact to hold hot plasmas in ring-shaped devices called tokamaks and in other magnetic traps. The goal is fusion energy squeezing light nuclei so they join and release energy, as in the sundae. Containing that hot, moving, charged soup is hard. The plasma pushes back with its own fields and develops waves and instabilities. It can kink, ripple, and snap in ways that need careful control. Some of the most beautiful natural patterns come from plasma physics. The aurora begins with the solar wind, a stream of plasma from the sundae. Earth's magnetic field guides some of those charged particles toward the poles. High in the atmosphere, they transfer energy to atoms and molecules. Oxygen gives green light at about 100–150 kilometers up, and deep red, higher still. Nitrogen and ionized nitrogen produce blues and purples. The result is a sky of moving arcs and veils, evidence that we live inside a magnetic shield that steers plasma every day. Plasma also drives solar activity. Solar flares and coronal mass ejections are sudden releases of magnetic energy and material. A key process is magnetic reconnection, where field lines break and reconnect, converting magnetic energy into heat and motion. When large ejections reach Earth, they can disturb satellites and power grids and also spark bright auroras. The sun's outer atmosphere, the corona, reaches temperatures of millions of degrees, much hotter than the visible surface below. How the corona gets so hot remains an active puzzle. Many ideas point back to plasma tiny flares, too small to see, waves that dump energy into the corona, and reconnection that heats plasma on many scales. Beyond our system, plasmas fill interstellar and intergalactic space. Radio jets from black hole regions carve plasma beams across thousands of light years. Shock fronts in supernova remnants accelerate particles to near light speed. In these places, plasma is not just common, it sets the rules for how matter moves and how energy spreads. Plasma is useful, too. Industry uses plasma cutting for fast, precise work on steel. Spacecraft can use plasma thrusters that push ions out the back to create gentle, efficient thrust for deep space travel. In medicine and manufacturing, cold plasmas can sterilize surfaces or change how materials bond, all without soaking them in harsh chemicals. In each case, turning a gas into plasma changes what is possible. Plasma asks us to rethink our simple ladder of states. Adding energy does not only make molecules move faster, it can change the kind of order a material supports. A gas can become a conductor, a wave carrier, a lattice of filaments that flicker and align with fields. The rules shift from neutral collisions to charged interactions. Matter remains matter, but it plays by a different set of cues. Now, turn to the opposite extreme. Instead of heating, imagine chilling atoms more and more. You slow their motion with laser light and magnetic traps. The temperature falls toward absolute zero, where random thermal motion is as small as nature allows. In that deep cold, a strange order appears. Atoms that once behaved like many separate walkers begin to act as one. This is the Bose-Einstein condensate, or BEC. The name is long, the idea is crisp. At very low temperature, certain atoms can occupy the same quantum state. Quantum means we must think in terms of waves, as well as particles. Each atom has a wave function, which is a way to describe where it is likely to be and how it moves. At normal temperatures, those wave functions overlap a little, but stay mostly separate. As the system cools, motion slows and the waves get broader. The spread increases until, instead of many small, private waves, the atoms share one large wave. Individual identity fades. The group behaves like a single quantum object. To make sense of that picture, keep the math in the background and focus on the steps. At room temperature, atoms jostle and collide. Their wave functions are narrow. Lower the temperature and the thermal jostling weakens. Each particle's wave function extends as if the fuzzy region that marks its likely position stretches out. As cooling continues, the spread becomes large compared with the spacing between atoms. Under the right conditions, the separate waves overlap in a way that locks their phase, a measure of the wave's timing, so the atoms move together. That lock is the condensate. What you can do with a BEC is equally striking. Because the atoms share one wave, the fluid can flow without friction in special settings, a behavior called superfluidity. It can creep along walls and through tiny channels without losing energy to ordinary drag. Light can pass through a BEC and slow down to walking speed in carefully tuned experiments because the shared wave responds as a whole. Tiny ripples, quantized vortices, can form in a rotating condensate, making patterns that reveal the fluid's deep order. Making a condensate is hard, and it happens in very controlled spaces. Vacuum chambers with extreme cooling and precise lasers. Yet the lesson reaches beyond the lab. Matter can become more solid, in one sense more coherent, more locked together by getting colder, not by getting harder. The path to this order is not pressure or a lattice. It is a wave joining other waves until they act as one. To take the first step into this cold world, Picture the last bit of heat being stripped away. Gas atoms sit in a trap of light. Lasers tuned just below an atomic transition pull on moving atoms, slowing them. Magnetic fields hold the cloud in place. Each stage trims energy. The cloud dims in the camera. The temperature falls into billionths of a degree above absolute zero. At that point, the classical picture cracks and the quantum picture takes over. The key idea is that lower temperature means less random motion. With less motion, the wavelength associated with each atom, the de Broglie wavelength, grows. You do not see a visible wave, but the math tracks the wave-like side of the atom's nature. As the wavelength grows, neighboring atoms' waves begin to overlap. In most systems at higher temperature, those overlaps shift and slip without building a stable pattern. In a condensate, the overlaps line up, and the system prefers a single, shared quantum state. From many, one. This shift is not a trick of words. It has measurable signs. The momentum distribution of the atoms sharpens. Interference patterns appear when two condensate clouds are released and cross. Much like light waves from two slits, the whole behaves like a single matter wave, with a well-defined phase across the sample. With that shared phase, the atoms respond to pushes and pulls in lockstep. This coherence is fragile if you add heat or disturb the trap, but while it lasts, it shows a kind of order, unlike the order of a crystal. Seen alongside plasmas and amorphous solids, a condensate rounds out a wider view. Matter is not only about hardness or flow, it is also about how particles share information and motion. Sometimes the rules are set by charges and fields, and the way a plasma holds structure in its glow. Sometimes the rules are set by frozen disorder, as in glass, and sometimes the rules are set by wave unity, as in a BEC. Each case is a different compromise among energy, motion, and interaction. The path to a condensate is a path of cooling and control. It begins with a normal gas, thins out its energy, and invites the atoms to adopt a common rhythm. That rhythm is the shared phase. When it locks, the crowd becomes a choir. The final steps happen when the temperature is so low that the thermal jostling no longer breaks the pattern. At that point, the many wave functions begin to spread out. Here's the key twist. Some particles are bosons, named after Satyendra Nath Bose. Bosons are allowed to share a quantum state. They do not follow the Pauli exclusion principle, the rule that keeps certain particles from occupying the same state. Fermions like electrons, protons, and neutrons do follow that rule and resist piling up in one place. Bosons are the sociable ones. When the temperature drops and their wave functions spread, they can overlap without complaint. Lower the temperature far enough, and a large number of bosons can settle into one and the same quantum state. At that point, the system does not act like many separate atoms that just happen to be close. It behaves as if it were one unified object. The particles become indistinguishable in practice. The system's behavior is described by a single wave function that covers the whole cloud. This is the Bose-Einstein condensate, a state first predicted in the 1920 seconds by Bose and Albert Einstein. The idea sat in theory for decades because the technology to reach such low temperatures and gentle control did not exist. The math was clear, the experimental path was not. That changed in the mid-1990 seconds. Using carefully tuned lasers and magnetic traps, researchers cooled a cloud of rubidium atoms to a few billionths of a degree above absolute zero. At those temperatures, random motion becomes tiny and the atomic waves spread wide. The team saw a sharp change in the momentum distribution, a signature that many atoms had fallen into the same quantum state. The condensate was no longer a thought experiment. It was a real, measurable state of matter. In a condensate, individual motion fades and collective motion takes over. Push one region, and the response appears across the whole sample. The system's phase, the timing of its quantum wave, stays aligned over large distances. That coherence leads to unusual effects. A condensate can show superfluid behavior, meaning it flows without friction in the right conditions. It can move through narrow channels that would stop an ordinary fluid. It does not fit the simple categories we use for solids, liquids, or gases. It behaves according to quantum rules scaled up to macroscopic size. BECs let scientists study quantum effects in clouds of many atoms rather than in single particles. Interference, tunneling, and long-range coherence, usually topics from small-scale physics, become visible in the lab. In one well-known demonstration, two condensates were allowed to expand and overlap. The density pattern showed clean, repeating bright and dark bands. Those bands were not made by light. They were made by atoms acting as waves. The pattern was direct evidence that matter waves can interfere just like water waves or laser beams. Reaching a condensate is not as simple as making something cold in a freezer. The required temperatures are near absolute zero, roughly 273.15 degrees Celsius. Scientists begin with laser cooling, where atoms absorb and re-emit photons tuned slightly below an atomic transition. Because absorption happens for atoms moving toward the light, the process saps kinetic energy and slows them down. Then comes evaporative cooling in a magnetic or optical trap. The most energetic atoms are allowed to escape, and the remainder re-equilibrate at a lower temperature. Step by step, the cloud loses heat until the conditions for condensation are met. The result is delicate. Heat, stray light, or vibrations can disturb the shared phase and break the condensate apart. While it is stable, the system functions as a single quantum object with a measurable size. Researchers can shape it with light, split it, recombine it, and time its response. Because the phase is well defined across the cloud, measurements can be very precise. The condensate becomes a tool, not just a curiosity. The broader idea is simple. As energy drains away and motion slows, order of a new kind appears. It is not the order of atoms locking into a crystal lattice. It is the order of many waves lining up. When that happens, individuality in motion is replaced by a common rhythm. The system trades random movement for coherence. The change is reversible if you add heat, but while it lasts, it reveals how quantum rules can govern a large, visible sample. BECs have also become model systems for questions beyond atomic physics. Researchers use them to explore quantum phase transitions, where the ground state of a system changes as a control parameter, like interaction strength, is varied at zero temperature. They build analogs of horizons and study how waves behave near them, drawing connections to black hole physics. Because the system's parameters are adjustable, it serves as a clean testbed where predictions can be checked and new effects can be found. None of this would have moved from theory to practice without early insights into indistinguishable particles. Bose's work on light-treated photons has identical quanta that can share states. Einstein extended those ideas to atoms. Decades later, with new lasers, better vacuum, and precise magnetic control, The predicted state appeared in the lab. The chain from idea to device was long, and each link required both imagination and careful engineering. Now take the idea of frictionless flow and look at it in a different setting. Superfluids. Picture a liquid set into motion in a ring. In an ordinary fluid, viscosity internal friction turns organized flow into heat, and the motion dies away. In a superfluid, that does not happen. The flow can persist with no measurable loss. Viscosity, as we usually define it, drops to zero for the component that is superfluid. Helium-4 is the classic case. Cool liquid helium below, about 2.17 Kelvin, and it undergoes a transition into a superfluid phase, often called helium-2. To the eye, it still looks like a clear, cold liquid. Its mechanical behavior is different. One striking effect is the fountain effect. Put a fine capillary into a bath of superfluid helium and heat the capillary tip gently. Helium streams upward through the capillary and out, as if pushed by an unseen pump. The motion is driven by differences in chemical potential associated with temperature, not by usual pressure gradients. Superfluid helium can also climb walls in a thin film. A microscopic layer forms on surfaces and can flow up and over the rim of a container. The film does not stop at the edge because the superfluid component faces no viscous penalty for moving, and the system seeks to equalize the chemical potential. The same lack of resistance allows the liquid to leak through tiny pores that would block ordinary liquids. Containment becomes a design problem. Even small imperfections can act as paths. Quantum rules set the stage for these behaviors. At low temperature, a large fraction of helium, 4 atoms, occupy the lowest energy state allowed by the liquid, resulting in long-range phase coherence. The flow becomes quantized. That means circulation can take only specific values, rather than any value in a continuous range. Stirring the liquid does not produce random, decaying eddies. Instead, it produces quantized vortices, small, stable whirlpools with a fixed amount of circulation. They persist because there is no viscous path to damp them out, and interactions between vortices follow clear, simple rules compared with ordinary turbulence. The persistence of motion is not just a slogan. In experiments with torus-shaped containers, superfluid helium has been seen to maintain flow for very long times without slowing. The timescales can be hours, days, or longer, limited by imperfections or interactions with any remaining normal, non-superfluid component. The system acts like a frictionless flywheel for fluid motion. Superfluid behavior is not limited to helium-4. Helium-3, an isotope with one fewer neutron, also becomes superfluid, but its path is different. Helium-3 atoms are fermions. Fermions cannot crowd into the same quantum state the way bosons can. To reach a superfluid phase, helium-3 atoms pair up in a way that changes the effective statistics, similar to how electrons pair in a superconductor. These pairs act as composite bosons. The transition occurs at even lower temperatures, fractions of a Kelvin, and the resulting superfluid has multiple phases with distinct internal structures and properties. Each phase reflects a different way the pairs organize their spin and orbital motion. The details are rich, and the temperature control must be extremely precise to map them. What ties BECs and superfluids together is coherence. In a condensate, bosonic atoms share one state. In helium-4, a large part of the liquid's atoms behave in lockstep, giving rise to frictionless flow and quantized vortices. In helium-3, pairing creates the conditions for superfluidity, even though the atoms are fermions. In each case, a macroscopic quantum order emerges when thermal motion is reduced enough for quantum statistics to dominate. The experimental tools that make these studies possible are precise and layered. Laser cooling takes advantage of momentum exchange between photons and atoms, trimming motion in controlled directions. Magnetic and optical traps confine the atoms without touching them. Evaporative cooling chooses the hottest atoms to remove and lets the rest settle at a lower temperature. For helium, reaching the needed temperatures relies on cryogenic methods such as pumping on liquid helium to lower its boiling point, using dilution refrigerators for ultra-low temperatures, and designing containers that minimize heat leaks. The measurements are equally careful. Time-of-flight images capture the momentum distribution of atoms released from a trap. Interferometric setups reveal phase coherence by overlapping two matter waves. In superfluids, second sound waves, temperature waves distinct from ordinary pressure waves, carry information about the fraction of the liquid that is superfluid. Observing tiny jets in the fountain effect or thin films creeping over edges requires clean apparatus and stable conditions. These systems also provide analogs and tools for other areas. Quantized vortices help researchers study turbulence in a simpler, more controlled form. Stable, long-lived flows in rings connect to ideas in precision sensing. The sensitivity of a condensate's phase makes it a candidate for gyroscopes and gravity probes. In helium-3, the detailed structure of the superfluid phases offers a window into symmetry breaking and topological order, themes that appear across modern physics. What stands out is how far the basic idea goes. Change the temperature, adjust the interactions, and matter shifts into new regimes with new rules. A gas of bosons becomes a single, coherent wave. A liquid of helium-4 moves without friction and supports vortices that never smear out. An isotope of helium pairs up and builds a more complex superfluid with several distinct phases. Each step keeps to the same core laws while revealing different patterns those laws can support. Returning to the image of a liquid in a bowl, an ordinary fluid spreads and settles. A superfluid can climb and escape through films or pores, not because it ignores gravity, but because its allowed motions and energy landscape are different. The lack of viscosity and the presence of quantized flow change what is stable and what is not. The effects are subtle in appearance, but strong in principle. Helium-4 shows the classic version of this physics near 2.17 K. Helium-3 shows a different route at much lower temperatures, where pairing and internal symmetry matter. In both cases, the behaviors are testable and repeatable, not magic tricks. They are the macroscopic footprints of quantum statistics and coherence, made visible when thermal noise is pushed down far enough. While superfluidity in helium-4 arrives because bosons can share a state directly, helium-3 must build pairs before that shared behavior can emerge. That need for pairing shifts the critical temperature downward and makes the phase diagram more intricate, with distinct phases that respond to fields and motion in their own characteristic ways. It has multiple phases, each with its own internal structure and behavior. It's as if helium-3 decided that one form of superfluid just wasn't enough. Superfluids are surprising, but there is a step that sounds even stranger: supersolids. A supersolid combines two traits that seem incompatible. It has the repeating structure of a solid atoms arranged in a regular lattice, while also showing frictionless flow like a superfluid. It keeps shape, and, in the right way, it flows. For many years, this idea was debated. Early hints in helium drew attention. but the data were hard to read, and arguments went back and forth. Clearer evidence arrived in the 21st century with ultra-cold atoms and precise controls. In one line of experiments, physicists trapped a cloud of very cold atoms and used lasers to tune how the atoms interact. Under those settings, the atoms formed a standing pattern of higher and lower density, like a crystal. At the same time, the cloud kept a single quantum phase across the pattern, a sign of coherent flow. The system knew about the grid while still moving in a way that did not cost energy to internal friction. The atoms did not march out of place. The flow was through the shared wave that linked them. This behavior comes from quantum mechanics plus interaction strength. The waves linked to each atom overlap and interfere. The overlap can lock in a periodic density pattern while keeping the phase ordered across the sample. That gives both rigidity and flow in one state. Language struggles here because our usual labels split solid and fluid into separate bins. At low temperatures, and with the right interactions, matter can bridge those bins without breaking the basic rules. The lesson is broader than one system. Superfluids and supersolids show that what matter does depends on conditions. The same atoms that bounce freely at room temperature can act together when cooled and confined. The same helium that fills a party balloon can, under special conditions, stream without loss or settle into patterns with quantum order. These behaviors are not just curiosities. Understanding superfluid flow helps with cryogenic design and precision sensors. Long-lived coherence matters for quantum devices where keeping a stable phase is key. Supersolids, a newer frontier, may reveal fresh kinds of collective order and point toward materials that couple stiffness and flow in useful ways. Even without an immediate device in mind, these states hold attention because they show quiet motion with rules that are clear and testable. A system can keep its place and still move through the shared wave that binds it. That picture may feel unusual, but it fits the data and the math. It tells us that solid and fluid are not always opposites. Under the right limits, they can be partners. Now wind the clock far back, far beyond stars or even atoms. In the first few microseconds after the Big Bang, the universe was hot and dense, beyond anything we touch today. Under those conditions, the matter we know could not hold together. Instead of protons and neutrons, there was a short-lived state called quark-gluon plasma. To reach that idea, zoom inside ordinary matter. Protons and neutrons sit in the nucleus of an atom. Each one is made of quarks, bound by the strong force. The strong force is carried by gluons. At normal energies, quarks and gluons are confined. They do not roam free. The binding is tight, like a net that pulls harder the more you stretch it. Heat the system to trillions of degrees, and the picture changes. At those extreme energies, the force is screened, and the quarks and gluons move independently. The bound states melt into a hot, dense fluid of quarks and gluons. That fluid is the quark-gluon plasma. You might guess that such a high-energy soup would behave like a thin, chaotic gas. Measurements show the opposite. Quark-gluon plasma flows like a near-perfect liquid with very low viscosity. It expands smoothly and carries collective motion across the tiny drop formed in a collision. In some comparisons, it outperforms superfluids in the cold by coming closer to the lower bound on viscosity set by theory. The hottest stuff we can make turns out to be one of the smoothest flowing. Creating this plasma on Earth takes heavy ion colliders. At places like the relativistic heavy ion collider in New York and the Large Hadron Collider at CERN, Heavy nuclei, gold or lead, are accelerated to near light speed and smashed together. In the instant of overlap, energy density spikes. For a fraction of a trillionth of a second, the nuclei melt and form a tiny droplet of quark-gluon plasma. It then cools and turns back into hadrons, particles like pions, protons, and neutrons, as the strong force pulls quarks into bound states again. Physicists read these events by tracking thousands of particles that fly out as the droplet freezes. The pattern of directions and speeds records how the fluid expanded. These flow measurements tell us about the plasma's viscosity and how it responds to pressure. From that, we learn about the strong force in a regime that is impossible to study in any other way. The data connect to the early universe, where a much larger and longer-lived version of the same plasma filled space before it cooled into the building blocks of matter. Quark-gluon plasma also touches deep questions about symmetry. The Big Bang should have made matter and antimatter in equal amounts. Today we see matter winning by a large margin. The exact reason needs physics beyond simple heating, yet the extreme conditions in and near the quark-gluon plasma phase may have set the table for the processes that tipped the balance. By checking how the plasma behaves and how tiny differences can grow, scientists refine the story of how the early universe moved from symmetry toward the matter-dominated world we observe. This plasma is brief. It forms and cools within microseconds in the early cosmos, and within less than a trillionth of a second in a collider. As it cools, the strong force tightens, and hadronization begins. Quarks lock into pairs and triplets, and the familiar family of hadrons appears. Protons and neutrons are among the early results, setting the stage for light nuclei to form minutes later when conditions allow. From there, the long path to atoms, stars, and planets follows. The extreme state may not be entirely a thing of the past. Inside neutron stars, city-sized remnants of massive stars, the density is so high that the inner core could host forms of matter where quarks are less tightly confined than in ordinary nuclei. There is even a proposal for quark stars, objects denser than neutron stars, where quark matter fills the core or the entire body. These remain hypothetical, but observations of mass, radius, and cooling behavior keep the search active. If such objects exist, they would be cosmic samples of high-density quark matter, frozen records of conditions not far from those after the Big Bang. Gluons sit at the center of all this. They carry the strong force and keep quarks bound at ordinary energies. The strong force is powerful, far stronger than electromagnetism at nuclear distances, but it drops off quickly with range. At high temperature or density, screening effects weaken confinement enough to let quarks and gluons move within the plasma. As the system cools, confinement returns. You can think of it as an elastic system with a sharp reset. Stretch hard enough, and the net opens. Relax, and it snaps shut. The return to bound states is rapid, which is why the plasma exists only for a blink. It is useful to keep the scale in mind. Temperatures in collider-made quark-gluon plasma reach several trillion Kelvin. That is far above the center of any star. The droplets are tiny, smaller than a nucleus, and live for extremely short times, but they carry clear signatures. The shapes of the particle sprays tell us the fluid was there and that it flowed. The relative numbers of particles tell us how it cooled and recombined. Each collision is a small replay of the universe's first instant. These studies remind us that the particles we take as basic are built from even smaller parts. Protons and neutrons are not indivisible. They are stable bound states that formed as the universe cooled. The matter in your body is, in that sense, the cooled and confined remnant of an earlier, hotter phase. Day to day, we live at room temperature and standard pressure, where atoms are calm and chemistry works. The history of those atoms includes a time when the same ingredients were free in a hot fluid ruled by the strong force. Quark-gluon plasma research pushes the limits of both theory and equipment. It needs high vacuum, strong magnets, fast detectors, and careful statistics. It also needs clear ideas about how the strong force behaves as conditions change. Two key ideas help. Confinement explains why we do not see free quarks at low energy. The force grows with separation. Asymptotic freedom explains why, at very high energy, the strong force gets weaker, and quarks behave almost like free particles for short times and distances. The plasma sits in the crossover, where quarks are not locked in hadrons, yet interactions are still strong enough to create a liquid with collective flow. By building and analyzing this state, we learn not just about early times, but about the range of what matter can be. Near absolute zero, atoms can join a single wave in a Bose-Einstein condensate. At a few Kelvin, helium can flow without friction as a superfluid. In special settings, a system can be both ordered and flowing as a supersolid. At the other extreme, at trillions of Kelvin, quarks and gluons make a hot liquid with tiny viscosity that expands and cools into the blocks of ordinary matter. Across all of these cases, the rules are the same. The outcomes differ with temperature, density, and interaction strength. The strong force is at the heart of the hot case. Gluons do not only transmit it, they also carry color charge themselves, so they interact with one another. That self-interaction is part of what makes the theory rich and the plasma behave like a liquid. When energy is high, the effective grip loosens. When energy drops, the force locks quarks into hadrons very quickly. Without gluons, quarks would not bind into protons and neutrons. Without those bound states, atoms would not exist. It is striking to realize that protons and neutrons, the sturdy cores of atoms, are products of cooling. They were not present in the earliest instant. They emerged when the fire eased enough for binding to work. We live comfortably near 20 degrees Celsius while carrying matter that, by its deep history, once traced back to conditions millions of times hotter than the center of the sundae. The everyday world is quiet only because the early heat faded and the strong force did its binding when the universe allowed it. Quark-gluon plasma is brief, hidden inside collider events, and invisible to the eye, yet its role is huge. It holds clues to how the early universe cooled and organized, how raw energy condensed into particles, and how a hot, uniform state gave way to structure. It is the nearest portrait we have of the cosmos. Before protons and atoms could exist, a moment when everything was free, fast, and extremely hot, waiting to become something more. Now picture a pendulum that never slows, not because it draws power from a motor or a spring, but because it simply keeps swinging on its own. That sounds like a violation of basic physics, the kind of perpetual motion that does not exist. In quantum physics, though, there is a close cousin to that idea: time crystals. The name suggests science fiction, but they are real phases of matter with unusual order. A normal crystal repeats in space. Its atoms form a pattern that tiles a lattice again and again. When a crystal sits in its lowest energy, or ground state, nothing changes in time. The pattern is fixed. A time crystal repeats in time. Its internal state cycles with a steady beat. Even when it is as low in energy as it can be, the system shifts between configurations in a regular rhythm. The system ticks without using energy the way a machine does. The idea was proposed in 2012 by Frank Wilczek. The question was simple to ask and hard to judge. Could a quantum system show periodic behavior in time the way a crystal shows periodicity in space? Physicists worried about energy conservation. The proposal was not a plan to make energy from nothing. It was a claim that, under the right conditions, a system could have a stable motion built into its lowest energy behavior. The motion would be protected by symmetry and by the details of the interactions, not powered like a motor. For a few years, the idea lived mostly on paper. Then experiments began to find a concrete version called a discrete time crystal. These are systems that are driven by a periodic kick, such as a train of laser pulses or a repeated set of microwave operations. A normal driven system echoes the drive. Kick it every t seconds, and it responds every t seconds. A discrete time crystal breaks that timing. Kick every t, and the system settles into a steady response every 2 tons, or another multiple, and it keeps that subharmonic rhythm without drifting. It is as if you tap a table once every 2 seconds and the table answers with a stable beat every 4 seconds, on and on. This matters because the pattern is not a simple copy of the input. The system finds its own tempo and locks to it. In many body settings, collections of many interacting particles disorder and a phenomenon called many body localization can keep the energy from spreading and heating the system. The drive keeps time, but it does not pump the system into a hot, featureless state. Instead, the ordered rhythm persists. Different platforms have made time crystals. Chains of trapped ions use laser pulses to flip and interact qubits in a repeating sequence. Nitrogen vacancy centers in diamond use microwave drives to create and read out subharmonic responses. Superconducting qubits arranged on a chip can be programmed to follow a pattern of gates that shows robust period doubling. In one high-profile result, a quantum processor called Sycamore used carefully designed pulses to flip between states with a stable rhythm that resisted noise for many cycles. The device did not run on free energy. Rather, its pattern was protected by the structure of the driven system. To make sense of the words, unpack a few key ideas. A ground state is the lowest energy configuration a system can reach. In a time crystal, we talk about a Floquet ground state, meaning the steady pattern of a periodically driven system. Subharmonic response means the system repeats only after multiple drive periods. Many body localization means that disorder plus interactions can trap energy locally so it does not smear out as heat. Put these together and you can build a driven, many-body system that cycles in time in a stable way. Why is this not a loophole in thermodynamics? Because nothing is creating energy. The drive sets the timing and the system's structure chooses a rhythm that is stable to small imperfections. The motion is internal and rhythmic, a protected change of state that repeats. It is not a wheel that turns to do work. It is a pattern that persists, because the system cannot easily move to other patterns. Time crystals are young as a field, but potential uses are visible. A stable, repeating pattern can help in keeping time, reducing certain kinds of noise, or storing quantum information in forms that resist decoherence. Periodic order in time could act as a reference the same way a spatial crystal provides a clean template for electrons. Even if practical devices are far away, the concept widens how we think about order. Stillness is not the only kind of stability. A rhythm can be stable, too. The contrast with other exotic phases helps. A superfluid shows motion without friction through space. Its flow can persist. A time crystal shows motion in time without decay of the pattern. Its beat can persist. One is about how a fluid moves. The other is about how a state cycles. Both rely on quantum coherence and on limits where disorder and noise do not easily destroy the order. There is also a broader lesson about symmetry. Ordinary crystals break continuous translation symmetry in space, slide by a tiny amount, and the pattern does not match, but slide by a lattice spacing, and it lines up. Time crystals break time translation symmetry of the drive, shift by one drive period, and the state does not match, but shift by 2 periods or more, and it does. Breaking symmetry often creates new modes, collective motions, like the vibrations in a solid. In driven systems, time symmetry breaking can create robust cycles that are easy to read and hard to scramble, which is useful both for basic science and for devices that need steady references. Making these systems work demands careful engineering. Trapped ions need ultra-high vacuum, stable lasers, and precise timing. Superconducting qubits need cryogenic temperatures, clean fabrication, and low noise control electronics. Imperfections cannot be eliminated, but the hallmark of a time crystal is that the subharmonic signal remains stable across many cycles despite those imperfections. When the pattern holds up as the system size grows or as small changes are made, researchers gain confidence that they are seeing a true phase, not a transient trick. As we widen the catalog of phases, superfluids, supersolids, quark-gluon plasma, time crystals, the common thread is not one substance but the conditions: temperature, density, interaction, strength, drive, and disorder set the stage, change the stage, and familiar particles arrange themselves in unfamiliar ways. Sometimes order appears at extreme cold, when motion slows and waves line up. Sometimes order appears at extreme heat, when a fluid of quarks flows with tiny viscosity. And sometimes order appears in time, where a system finds a repeating beat and holds it. There is a human side to this story. New phases often start as ideas that sound odd. They move to simple toy models, then to careful designs, then to first signals, then to stronger proofs. Along the way, methods improve and the language sharpens. Time crystals followed that path from proposal to demonstration to expanding platforms. The pattern will likely repeat as researchers test how robust these cycles can be and whether they can be braided with other kinds of order. Even if time crystals never leave the lab, they have already shifted the way we think about equilibrium and motion. A ground state can be dynamic under periodic driving. Order does not have to be a static pattern in space. It can be a steady rhythm in time. That point matters in an era when quantum systems are being built, tuned, and used as tools. The ideas also connect back to the earliest times. The young universe expanded and cooled, and in doing so it passed through phases with different symmetries. Patterns in the cosmic microwave background and in the distribution of galaxies reflect how those phases left their marks. While a time crystal is a laboratory construct, it reminds us that symmetry and its breaking can organize behavior across scales, from qubits on a chip to fields in the sky. None of this overturns the rules of physics. It deepens them. Motion can be stable. Change can be ordered. A state can remember a beat the way a crystal remembers a spacing. These are not loopholes. They are options that the laws allow when conditions line up. Time crystals do not let you travel in time. and you will not find them in rocks. They are patterns of evolution in carefully prepared quantum systems. Their value is in what they reveal. Another way matter can arrange itself, another route to stability, another handle for controlling quantum information. They are examples of how listening closely to a system, nudging it, measuring it, and learning its rhythm can uncover order where we did not expect it. And now, from hidden rhythms to everyday puzzles, consider the small riddle of a stubborn source. There's something delightfully mischievous about ketchup. You tip the bottle, give it a gentle shake, and nothing. Then, with a little more encouragement, it finally lets go and splatters across the plate in one wild blob. It isn't being stubborn for fun, even if it feels that way. Ketchup, along with toothpaste, slime, custard, yogurt, paint, and more, doesn't follow the neat rule that a liquid flows the same no matter how you push it. These are non-Newtonian fluids, and they bend the usual link between push and flow. Start with Isaac Newton's simple picture for ordinary fluids. In a Newtonian fluid, the viscosity, its internal thickness, stays constant. Water is the classic case. Pour it gently or stir it hard. The resistance you feel is roughly the same. Honey is thicker than water, but still Newtonian. Double the push, double the flow rate. Non-Newtonian fluids break that link. Their viscosity changes under stress. Some get thinner when stirred or shaken. Others harden when hit. Some stretch slowly but snap if pulled fast. Our everyday world is full of them once you know what to look for. Take oobleck, a mix of cornstarch and water you can make at home. Stir it slowly and it oozes like a liquid. Slam it with your hand and it behaves like a solid. The reason lives in its microstructure. Cornstarch grains are suspended in water with only a small gap between them. Move slowly and water can slide between the grains, letting them rearrange. Hit it quickly and the grains jam together, building a temporary scaffold that resists motion. This is shear thickening. The harder you push, the thicker it gets. Picture a hallway full of people. If everyone walks calmly, you can weave through. If someone sprints, bodies jam and the flow stops. Other fluids do the opposite. Ketchup, shampoo, and many paints are shear thinning. Sitting still, their internal structure, entangled chains, tiny particles, or weak bonds keeps them thick. Agitate them and the structure loosens, so they flow more easily. That is why a ketchup bottle needs a shake before it pours, and why paint spreads smoothly under a roller, yet doesn't drip like water when left alone. Engineers tune these recipes so the materials behave well in real use. Steady on the shelf, smooth in motion. Some materials are both fluid and springy. These are viscoelastic. Slime is a good example. Pull it slowly, and long chain molecules, polymers, uncoil and slide, so the slime stretches. Yank fast, and the chains don't have time to move past one another. They resist, and the slime snaps. Bread dough, chewing gum, and even silly putty show the same push and weight behavior. No single label captures them. Time matters as much as force. Gels push the idea further. A gel is mostly liquid trapped in a solid-like network. Think of hair gel, gelatin desserts, or soft contact lenses. The liquid water can move locally, but a web of molecules or particles forms a cage that holds the shape. Tap a gel and it wobbles because the network stores and releases energy like a spring. Warm it, change the salt level, or add an acid, and the network can weaken, letting the gel relax or even melt. Amorphous solids sit near this family. Unlike crystals, which have atoms in repeating patterns, amorphous solids lack long-range order. Glass, many plastics, waxes, and some rubbers fit here. At room temperature, they hold shape, yet under heat or long stress, they can creep or flow very slowly. Their solidity is real, but conditional. This reminds us that labels like solid and liquid are not hard walls. They are zones of behavior. Biology also lives in this messy middle. Blood is shear thinning, which helps it flow through narrow vessels. Mucus and saliva are viscoelastic, which helps protect and lubricate tissues. Egg whites change texture with stress and heat as proteins unfold and link together. Wet sand stiffens under your feet when you walk quickly because the grains jam and the water between them cannot escape fast enough. The same beach feels soft when you stand still. These materials are not just curiosities, they are tools. Body armor made from shear thickening fluids stays flexible in normal use, but hardens on impact, spreading the force. Shock-absorbing foams and pads use viscoelastic designs to soak up energy. In factories, non-Newtonian paints and inks reduce spatter and improve finish. In food science, rheology, the study of flow and deformation, guides the feel of sauces, yogurts, and ice creams. In geophysics, it helps model landslides, mud flows, and the slow creep of glaciers. In medicine, it informs how drugs spread in gels and how blood moves through stents. The point that ties this together is simple. Behavior depends on structure and timescale. The same push can give different responses depending on how fast and how far you push and on what the material looks like inside. Chains can untangle or jam, particles can line up or lock, bonds can break and reform. When a bottle of shampoo suddenly gushes, or when a bowl of oobleck fights your spoon, you are feeling microstructure in action. Now, take a very different turn from squishy flows to shapes that don't care about stretching. Topology is a branch of math that tracks properties that survive smooth bending and twisting without cutting or gluing. A donut and a coffee mug are the same, topologically, because each has one hole, the donut's center and the mug's handle. Pinch, stretch, or reshape either one, and the count of holes doesn't change unless you tear it. That simple idea turns out to matter in quantum materials. In the 1,980 seconds, physicists explored electrons, confined to move in a thin, flat layer at very low temperature under a strong magnetic field. The result was the quantum Hall effect. As they changed the field, the electrical conductance across the layer didn't slide smoothly. It jumped in precise steps, flat plateaus, with values that were exact to many decimal places. Scratches, bumps, or impurities couldn't spoil those numbers. The system's behavior was pinned by a topological quantity, a number that counts how the electron states wrap around an abstract space defined by their motion in the field. You can ruffle the surface, but you can't get rid of the hole without tearing the fabric. That discovery opened the door to topological phases of matter states, defined not by local symmetry breaking, like a magnet aligning spins or ice forming a lattice, but by global features of their quantum wave functions. One important family is topological insulators. In these materials, the interior, the bulk, resists current like an insulator, but the surface or edges conduct electricity very well. Picture a chocolate truffle that is quiet inside, but whose outer skin carries charge almost perfectly. That edge conduction is protected. Bend the sample, roughen the edge, or add small defects, and the current still flows along the boundary because the topological hole count hasn't changed. What protects it? At the boundary between two regions with different topological character, say a topological insulator, and ordinary vacuum special electronic states must appear. These states are locked by the system's topology and, in many cases, by symmetries like time reversal symmetry. Electrons at the edge can move with little backscattering because common types of disorder can't flip their direction without also flipping other protected properties, like spin, which is hard under those conditions. The result is robust conduction that survives noise that would wreck an ordinary surface state. This robustness makes topological phases attractive for technology. In quantum computing, we want states that hold information while ignoring local noise. Topological protection offers a path to that goal. Certain systems are predicted to host exotic quasi-particles, emergent excitations that are not basic particles like electrons, but collective patterns of many particles moving together. These quasi-particles can have unusual statistics, meaning the rules for swapping their positions are different from those for ordinary bosons or fermions. In some proposals, moving them around one another can store quantum information in a way that is naturally protected from local errors. The road to those ideas runs through the quantum Hall effect. Under the right conditions, very clean samples, low temperature, and high magnetic field, the Hall effect becomes fractional. Instead of conductance steps at whole numbers, you see steps at fractions. This signals that the electrons are organizing into a new kind of quantum fluid with strong interactions. In that fluid, excitations carry a fraction of the electron's charge. They are not literal pieces of an electron. They are ripples in a sea of electrons that behave as if they carry, say, 1/3 of the usual charge. A helpful picture is the stadium wave. No single person runs around the seats, but the pattern moves as if a thing were traveling. In a fractional quantum Hall state, the pattern of many electrons moving together creates excitations that act like particles with fractional charge and sometimes with exotic exchange rules. Because these features are topological, they are stable against small changes in the environment. You can dent the sample or add weak disorder, and the key numbers do not shift. Topological ideas also explain why some materials conduct only on their surfaces even without a magnetic field. Spin-orbit coupling and interaction that links an electron's spin to its motion can make the band structure twist in a way that gives the bulk a hole count, different from ordinary insulators. At the boundary, the mismatch forces the appearance of conducting surface bands that cross the energy gap. Those bands are helical. Electrons with opposite spins move in opposite directions, which suppresses backscattering from non-magnetic impurities. Again, the effect is not about local structure or a perfect crystal face. It is about global character encoded in the wave functions. Engineers are learning to stack and twist thin layers like graphene sheets at special magic angles to create flat electronic bands where interactions dominate. In some of these systems, insulating, superconducting, and topological behaviors appear in close reach of one another, tuned by electric fields and twist angles. That makes the lab a playground for phases once thought impossible outside extreme conditions. To keep the picture grounded, remember that a topological invariant is just a number that does not change under smooth deformations. In the quantum Hall effect, it is tied to how electrons' phases wind around as they move in the magnetic field. In topological insulators, it relates to how bands connect across the Brillouin zone, the map of allowed electron momenta in a crystal. The math can be heavy, But the physical message is simple. When that number differs inside and out, the boundary must host special states. Those states give protected edge or surface conduction. All of this shows another way that matter organizes, not by lining up atoms in neat rows, not by freezing motion to zero, and not by flowing without friction, but by tying the system's behavior to a shape in an abstract space that cannot be untied without a tear. That kind of order is global and resilient. It does not care about small dents. It cares about wholes. The most mind-bending part is that these global features can create excitations with properties no single electron has. In certain fractional quantum Hall states, the effective carriers behave as pieces of charge smaller than an electron's. They are emergent, like the stadium wave. You cannot dig into one and find smaller particles. The fraction lives in the motion of the crowd. These quasi-particles can carry charges of 1/3 or an electron's charge, depending on the system. Even more surprising are the predictions, and in some platforms, signs of anyons, quasi-particles that can exist in two-dimensional systems and that are neither fermions nor bosons. Swap two fermions, like electrons, and the wave function picks up a minus sign. Swap two bosons, like photons, and it stays the same. Swap two anyons, and the wave function can acquire a phase that is neither 0 nor pi, or even change in a way that depends on the path you take around one another. This behavior is tied to the topology of the space the particles live in. In 2 dimensions, paths can wind and braid in ways that have no simple 3-dimensional counterpart, and that winding can store information in a form that small bumps and scratches cannot erase. That is the seed of topological quantum computing. Instead of keeping a qubit state in the delicate orientation of a single particle, you would encode it in the braids of anyons' world lines, how their paths wrap around each other in time. Because a topological braid cannot be undone by a local poke, the information would be naturally protected against many small errors. You cannot see this protection with a microscope. Atoms do not line up into a telling pattern. The shape lives in the mathematics of the wave functions, in how they wind through abstract spaces that describe momentum and phase. Topological phases resist tidy placement in a table of materials. They ask for a different map, one that blends condensed matter physics, quantum mechanics, and geometry. Here, structure is defined less by where particles sit and more by how the system responds when you move them around, twist their phases, or push them around loops. In 3 dimensions, the story continues with new twists. Certain crystals host conducting states only on particular surfaces or lines. Magnetic materials can organize into skyarm ions, tiny whirlpools of spin that behave like particles and are protected by topology. It takes energy to unwind a skyrimion, so it can carry information robustly in a magnetic memory without being erased by small defects. Robustness is the headline. Ordinary conductors lose performance when they get dirty. Topological systems keep key features because those features are anchored in global properties. You can dent, bend, or dope the material within limits, and the protected edge states remain. When engineering needs stability, low error rates, low noise, this kind of baked-in performance is attractive. It is resilience by design, set by the twisty logic of quantum geometry rather than by perfect crystals. The ideas have spread beyond electrons. Photons can be steered through patterned materials to mimic topological edge channels. Light rounds corners and dodges defects, with little backscatter in topological photonics. Sound waves can be guided in topological acoustic lattices to travel along edges without reflecting from obstacles. Even mechanical structures, arrangements of springs and beams, can host protected modes that localize at edges or corners. Topology is a language for waves and constraints, and it shows up wherever waves move through a structure that can be twisted in abstract ways. All of it begins with a shift in viewpoint. Stop seeing matter only as particles at positions, and start tracking the shapes that their quantum states trace in hidden spaces. In those shapes, matter gains a memory not of a place, but of a path. That memory confers resilience. It tells us that some forms of order live not in visible patterns, but in connections, loops, and windings that persist even when the surface looks messy. If you are holding a smartphone or watching a flat panel, you are already using a state of matter that prefers the middle ground. Liquid crystals flow like liquids, yet keep orientational order like crystals. Their molecules are free to move from place to place, but their long axes tend to align, so there is a direction in the fluid that matters. Think of a crowd that drifts around a plaza, but, on average, all look the same way. This partial order is the source of their useful optical behavior. In most common liquid crystals, the molecules are rod-shaped. Heat them enough, and they behave like a normal liquid. Cool them into the liquid crystal range, and their centers still wander, but their orientations line up. That alignment can be controlled with small electric fields. In a liquid crystal display, transparent electrodes apply voltage across tiny pixel regions. The field rotates the molecules or changes how strongly they align. Because liquid crystals affect polarized light, this twist changes how much light passes through crossed polarizers in each pixel. With careful timing and color filters, the screen forms images. Every letter of text and every moving picture is driven by billions of molecules tilting together by fractions of a degree. The path to this technology started with a puzzle. In the late 1800s, Friedrich Rienitzer heated a cholesterol-based compound and found it did not jump cleanly from solid to liquid. Instead, it passed through a cloudy intermediate. That in-between phase launched a new field. Today, we sort liquid crystal phases into families. In the nematic phase, molecules share a common orientation on average, but their positions are disordered, like a box of matchsticks with a preferred direction. In smectic phases, the molecules still align, but also form layers, stacks that can slide past each other. In chiral nematic cholesteric phases, the aligned direction twists slowly from layer to layer, forming a helix. That helical structure reflects certain wavelengths and produces iridescent colors, which is why mood ring films change color with temperature as the pitch of the helix shifts. Liquid crystals occur in biology too. Cell membranes are liquid crystalline bilayers. Some tissues in the eye rely on ordered yet mobile arrangements of molecules to guide light. These systems show a theme: enough freedom to function, enough order to hold shape. Their tunability with small fields makes them energy efficient. Set a pixel's alignment and it stays put until asked to change, consuming little power in the meantime. The interplay between light and liquid crystals goes deep. Because the materials are anisotropic, their properties depend on direction. Light traveling through them can have its polarization rotated or delayed. Designers use this to build variable lenses, shutters, and filters. In research, liquid crystals can reveal hidden fields. For example, droplets with set boundary conditions develop internal patterns that map the direction of alignment, making invisible forces visible as textures under polarized light. There is also engineering inside the screen that the eye never sees. Aligning layers rubbed in specific directions set the initial orientation. Microscopic spacers keep the cell gap uniform, so the optical phase shift is even across each pixel. Thin film transistors switch fields on and off. The final calm image is the product of precise control over a soft material that walks the line between order and motion. Even with decades of progress, liquid crystals still offer surprises. New phases arise with bent core molecules or in confined geometries. In soft robotics, patterned liquid crystal elastomers bend or twist when heated or lit, acting like muscles without rigid joints. Sensors use liquid crystals to amplify small environmental changes into visible texture shifts. The frontier keeps moving because in-between materials can be tuned in many ways by fields, heat, light, or surfaces. If liquid crystals show how order and flow can coexist, water ice shows how one substance can reinvent structure many times. Ice in a glass is familiar, brittle, cold, and buoyant. That ordinary form is called ice. The H is for hexagonal. In it, water molecules arrange so that each oxygen bonds to 4 neighbors in a tetrahedral pattern, and those tetrahedra connect to make hexagonal layers. The open geometry lowers the density, which is why ice floats vital for lakes and oceans that freeze from the top. Change the pressure and temperature, and water finds new blueprints. Crystallographers have catalogued at least 19 distinct crystalline ices so far, each with a different arrangement. Some pack atoms more tightly, making denser ices that sink in liquid water. Others distort the hydrogen bond network into cubic or more complex motifs. Nature builds many of them in places we do not normally touch. High-pressure ices in the deep interiors of icy moons, or unusual forms that can be quenched in the lab by fast cooling or compression. There are also amorphous ices, solid water without long-range order common in the cold of space where molecules land on dust grains and freeze without time to rearrange. Ice E is the snowflake maker. Under the right supersaturation and temperature, water vapor deposits onto a seed crystal and grows branching arms that reflect the underlying hexagonal symmetry. Slight changes in humidity and temperature shift, which faces grow faster, producing plates, columns, dendrites, or needles. The delicate shape is a record of the path through the cloud. But step off the familiar path, and the catalogue widens. Ice-like, a cubic form, can appear at low temperatures. Ice 2, through Ice XV and beyond, occupy regions of the phase diagram at higher pressures or different thermal histories, each with its own pattern of oxygen positions and hydrogen order or disorder. These structures matter beyond lists. In the mantles of giant icy worlds, high-pressure ices may influence heat, flow, and convection. In the lab, different ices help test models of hydrogen bonding and proton motion. Some forms are proton-ordered, with hydrogen positions locked. Others are proton-disordered, with hydrogens hopping among allowed sites, leading to residual entropy even at low temperatures. There are even reports of unusual states where protons tunnel collectively, blurring the line between classical and quantum motion in a hydrogen-bonded network. Water's habit of forming an open lattice at low pressure explains several anomalies we meet every day. Liquid water is densest near 4 degrees Celsius, so a pond can circulate as seasons change. Ice I's lower density means ice insulates the water below, helping life survive winters. Pressure melting at skate blades and the complex flow behavior at grain boundaries give ice its slippery character. Each trait is a practical echo of a specific molecular arrangement. Scientists map these arrangements with diffraction, spectroscopy, and high-pressure cells that squeeze tiny samples between diamonds. The phase diagram of water a map of which structure wins at each pressure and temperature keeps expanding as techniques improve. Computer models, refined by data, predict yet more forms under conditions beyond current reach, adding to the sense that even simple water has a deep structural life. It is striking that a substance so common can carry so many blueprints. We pour it, freeze it, and boil it without a second thought, yet under other conditions it builds lattices we have never seen at the kitchen counter. The names and numbers can feel like a catalogue, but the motive is simple. Hydrogen prefers 4 partners in a roughly tetrahedral arrangement, and the rest is geometry, how to honor that preference while filling space under different pressures and temperatures. Each solution is a crystal with its own density and symmetry, and each shows up when the environment asks for it. The most familiar ice is still useful to consider. Its hexagonal symmetry shapes snow optics and the sparkle of frost. Its low density keeps polar seas from freezing solid. Its fragile hydrogen bonds make it stiff at one moment and ready to melt at the next with a small injection of heat. Look closely, and even a plain ice cube is a compromise among bond angles, thermal motion, and the need to tile space without strain. Water is not alone in its polymorph habit, but it is the everyday champion. The lesson carries through all of matter. The same atoms, under different rules, from pressure and heat, can write very different structures. Sometimes those structures make a fluid that flows without friction. Sometimes they make a crystal whose edges carry current while the inside is quiet. Sometimes they make a liquid that also keeps a direction. And sometimes, with water, they make many kinds of solid, each one with a unique crystal structure, like different architectural blueprints for stacking water molecules. Some of these ices are denser, some are more compact, and some carry symmetries so odd you might think a playful architect designed them. Take ice 2, for example. It forms at higher pressures than everyday ice and packs molecules more tightly. Its lattice is rhombohedral, a skewed, squashed box, where angles tilt away from right angles. Move deeper into the phase diagram and you meet ice V and ice VI, forms that appear under even greater pressures. Each forces water molecules into closer, more awkward arrangements while still honoring the rule that each molecule makes 4 hydrogen bonds. Keep squeezing and heating in the right way, and you reach ice 4. This one matters far beyond the freezer. Ice 7 is stable at high pressure and can survive at surprisingly high temperatures. That makes it a good candidate for the deep interiors of icy moons and water-rich exoplanets, places where a hot rocky core presses up against a thick mantle of high-pressure ice. Far beneath Europa's surface, or inside a super-Earth with a wet mantle, Ice 7 could be holding steady right now. Another curiosity is Ice XI. It is a ferroelectric phase, which means the tiny dipoles of the water molecules, little positive and negative ends, line up in a common direction. That alignment gives the crystal an internal electric field, like a set of molecular compasses pointing together. In yet another corner of the map sits Ice XIIs, which forms when you pressurize certain ices quickly at low temperature. It is metastable. It can exist for a while outside its usual home, a reminder that even ice can be rushed into a phase by history and then get stuck there. These strange ices are not just collectible names. Knowing their structures helps scientists model the deep layers of icy worlds. It improves our ability to predict how heat moves through a moon, how an ocean sits under a crust, and how a planet's magnetic field, or chemical cycling, might work. It also pushes our understanding of hydrogen bonding, the the gentle directional attraction that ties one water molecule to another. Hydrogen bonds govern the shape of ice, but they also guide protein folding, DNA pairing, and countless reactions in living cells. Map the limits of hydrogen bonding in ice, and you learn something about the limits of chemistry itself. Even so, water's wild family of solids looks tame when you try to freeze helium. Helium is the lightest noble gas, and it resists settling into a solid lattice. Cool it to a liquid, then to a colder liquid, and you still will not get a solid unless you add enormous pressure, tens of thousands of atmospheres. The reason is quantum zero-point energy, the lowest jitter a quantum particle can have. Helium atoms are so light that even near absolute zero their quantum motion is large. They wiggle in place with such vigor that attractive forces cannot lock them into a lattice at normal pressure. To build a solid out of helium, you must push hard enough to overcome that baseline motion. When helium finally does solidify, it forms a crystal like other substances, but its atoms remain unusually mobile. They can tunnel shift position through barriers they would not cross in classical physics. This mobility led to debates about supersolidity, a proposed phase in which a solid shows frictionless flow. Early results hinted that solid helium might do this. Later studies revised the claim, pointing instead to defects and grain boundaries as the cause of the strange signals. Still, solid helium is no ordinary crystal. It lets physicists probe quantum behavior in a system that is frozen by normal standards, yet still guided by wave-like motion. Other simple molecules also rearrange under pressure into unfamiliar solids. Methane and ammonia make multiple crystal forms in conditions like those inside giant planets. There is growing interest in superyonic ice, a state in which oxygen atoms lock into a lattice while hydrogen ions become mobile, zipping through channels like charges in a battery. Superyonic ice is both solid and liquid in a sense. The oxygen framework is stable, yet the hydrogens flow. This phase likely exists deep within Uranus and Neptune and could help explain their magnetic fields, which behave in ways that differ from Earth's. All this complexity comes from a very simple molecule, H2O. 2 hydrogens, 1 oxygen, a bent angle, and a dipole moment. Water can build open networks that make ice float, dense frameworks that sink, cages that trap gas molecules into clathrate, hydrates, and even glassy amorphous solids with no long-range order. Studying ice is not just about cold. It is about how matter chooses a structure when pressure, temperature, and time pull in different directions. Ice is active, not passive. It negotiates with energy and environment, sometimes landing in a neat crystal, sometimes in a hurried, metastable arrangement that holds for a season or an age. Helium adds a gentle counterpoint. It reminds us that freezing is not guaranteed. Quantum motion can keep a substance liquid long after common sense says it should be solid. When it finally freezes under extreme pressure, helium opens a window into quantum mechanics you can hold in a small cell. Step away from laboratories and kitchens, and out into the spaces between stars. In the vast stretches of a galaxy's arm, matter thins to a whisper yet keeps rich behavior. The interstellar medium, the ISM, is not empty. It is a mix of gas, dust, plasma, and magnetic fields. Here, density is so low that a living room's volume might contain only a few atoms, but stretched across light years, those atoms collect into clouds and filaments that shape how galaxies live and change. Hydrogen dominates the ISM. Sometimes it is neutral atomic hydrogen, sometimes molecular hydrogen, In cold, dense regions, ultraviolet light and shocks can strip electrons away, turning gas into plasma. Plasmas thrive in space. Stars are plasma, stellar winds are plasma, and many glowing nebulae are plasma. Because their particles are charged, plasmas dance with magnetic fields. They twist into filaments, form magnetic loops, and send waves racing across regions larger than solar systems. Neutral gas drifts. Plasma organizes itself with invisible lines of force. Dust floats among this gas. Not the soft dust of a shelf, but soot-like grains and tiny silicate rocks, often smaller than smoke particles. Dust affects starlight by scattering and absorbing it. It warms, cools, and shades. It offers surfaces where atoms stick and meet, making simple molecules and then more complex ones. Deep inside dark, cold clouds, dust helps gas lose heat, allowing gravity to pull matter inward toward star birth. These star nurseries' molecular clouds span dozens to hundreds of light years. They are cold, often near 10 Kelvin. Inside, gas moves slowly, and small clumps grow under gravity. Over millions of years, the densest clumps collapse, heat up, and begin fusion. A star turns on. The new star's light and winds push back on its birth cloud, carving bright edges and pillars while compressing some regions and dispersing others. One region can hold cold dust, warm gas, and pockets of ionized plasma all at once, with borders shaped by light, shock waves, and magnetic tension. Temperature in space can be tricky to think about. In physics, temperature tracks the average energy per particle. Heat content depends on both temperature and how many particles you have. A 1,000,000-degree plasma that is extremely diffuse can hold very little total heat. You could sit inside such a region and still freeze because there are too few particles to warm you. The opposite extreme exists in Bock globules, small, dense blobs that show up as ink-black spots against glowing backgrounds. Inside, the temperature can be only a few degrees above absolute zero. Molecules move slowly, and the stage is set for collapse into new stars if gravity wins the slow tug-of-war against pressure and magnetic support. On the surface of dust grains, in these cold places, interstellar ices form water, carbon monoxide, methane, ammonia, and more. Ultraviolet light and cosmic rays can spur reactions in these icy films, building more complex organics. When a young star heats its surroundings, the ices release their molecules into space. Some of that chemistry ends up in disks around stars, the raw material for comets and planets. The simple act of freezing and thawing on a dust grain can seed a solar system with molecules that matter later on. Zoom farther out, and you reach the intergalactic medium, the thin matter between galaxies and clusters. It is even more rarefied than the ISM, yet it holds a large share of the universe's ordinary atoms. Much of it is hot plasma, energized by shocks as structures form under gravity and by blasts from active galaxies. We see its presence indirectly in how it swallows certain wavelengths from background sources and in its glow at X-ray and radio frequencies. Even in the emptiest places we can picture, matter persists, and it keeps records of cosmic events in its temperature and motion. Cosmic rays thread through all of this. They are high-energy particles, mostly protons and nuclei, launched by supernova remnants, jets from black holes, and other extreme engines. When they strike atoms or grains, they can break bonds and start reactions, changing the chemistry of a cloud. They ionize gas in places where starlight cannot reach, altering how magnetic fields couple to matter. The quiet look of a dark cloud often hides a busy chemistry lab driven by invisible particles. Across space, phases are not strict boxes. A region can be partly ionized, partly molecular, and peppered with dust. A shock can turn cold gas into hot plasma in a moment. A cooling flow can turn hot plasma into warm gas over eons. Magnetic fields and turbulence change the script, guiding flows along some directions and resisting compression along others. The result is a slow dance with many partners: gravity pulling inward, pressure pushing outward, radiation carving and heating, fields twisting and tying. The ISM reminds us that hot and cold, solid and gas are useful words, but not full maps. A plasma can be hot and harmless to touch because it is thin. A cloud can be cold and yet thick enough to block starlight. Ice can coat a grain in deep space, carry complex molecules, and later evaporate into a disk that makes comets and planets. A single patch of sky can hold almost every phase we have named in this journey, stacked along the line of sight like a layered landscape of invisible physics. The variety extends beyond galaxies. In galaxy clusters, hot intergalactic plasma battles gravity. Jets from central black holes blow bubbles in the plasma, and those bubbles rise like balloons, stirring the medium. Shock fronts race across millions of light years. Magnetic fields thread the volume. Each of these elements changes how the plasma cools and whether it can condense into stars again. Even at the biggest scales, the same themes repeat: temperature versus density, order versus flow, and the steady influence of fields and waves. We keep adding phases to our list: Bose-Einstein condensates, superfluids, supersolids, quark-gluon plasma, time crystals, topological phases, liquid crystals, superyonic ice, and we still cannot claim the list is complete. Nature rarely honors our tidy inventories. Move to a new corner of the map: colder, hotter, denser, more dilute, more strongly driven, and matter finds a new compromise. Some of those compromises are waiting in deep planetary mantles where pressure bends chemistry into new patterns. Others hide in neutron star crusts where nuclei form lattices in seas of superfluid neutrons. Still others may live in lab-grown materials where electrons feel engineered landscapes and adopt topological rules that are hard to scramble. The pattern that emerges is not a single rule but a way of thinking. A phase is a style of order. Sometimes it is the alignment of molecules into a lattice. Sometimes it is a shared quantum wave that sets many particles moving together. Sometimes it is a shape in an abstract space that protects edge states. Sometimes it is the mobility of one part of a crystal while another part stays fixed. And sometimes it is the balance of charge and field in a plasma stretching from star to star. Wherever conditions shift, new styles of order appear. Out in the quiet between stars, matter drifts in forms that ignore our kitchen sense. Gas slips into plasma. Dust gathers and cools. Ice grows, reacts, and releases cargo when a star lights up. Clouds collapse into stars. Then those stars blow winds and launch shocks that carve the next generation of clouds. Across this cycle, phases are not simply labels on a chart. They are the working modes of matter as it builds and rebuilds the structures we see. The more closely we look, the more likely it seems that there are phases we have not yet named hidden in the harsh cores of giant planets, in the dense skins of neutron stars, in new materials that twist electrons into protected flows, or in quantum systems driven just so, where motion is stable and order repeats in time. begin with a curious figure from two-dimensional physics, the ennion. Everyday matter is built from fermions and bosons, two well-behaved families with clear rules. Fermions, like electrons, refuse to share the same quantum state. Bosons, like photons, happily pile together. In flat, strictly two-dimensional systems, the rules loosen just enough to allow a third option. Ennions can carry fractional spin and follow fractional statistics. Swap two fermions and the wave function flips sign. Swap two bosons and it stays the same. Swap two ennions and the wave function can pick up an arbitrary phase. The system remembers the path you took during the swap. That history matters, and it can be used. That memory makes ennions promising for topological quantum computing. Instead of storing information in a fragile orientation of a single atom or electron, you store it in the braid of paths that ennions trace as they move around one another. Local bumps, scratches, and small errors cannot easily undo a braid. The information lives in the topology of the motion, not in a single spot. You cannot photograph this with an ordinary microscope. The atoms do not rearrange into a telling pattern. The order is encoded in the mathematics of many particles acting together. Do onions exist in the wild? Not in everyday materials on a table, but in special engineered settings. The fractional quantum Hall effect electrons squeezed to a thin layer, chilled to low temperatures, and placed in very strong magnetic fields creates a quantum fluid where excitations act like particles with fractions of the electron's charge. These excitations are quasi-particles, not new fundamental bricks. They are ripples of many electrons moving in a coordinated way, yet they can be tracked, counted, and made to interfere. Emergent does not mean imaginary. It means collective. Now step deeper into dense matter and a more speculative idea, strange matter. Ordinary nuclear matter is built from up and down quarks bound into protons and neutrons. Under extreme pressure, theory suggests that up and down quarks could mix with strange quarks and form a denser, possibly more stable phase, strange quark matter. In the cores of neutron stars, where densities crush matter into city mass objects only tens of kilometers wide, conditions may favor such a phase. If it forms and holds, a neutron star could convert into a strange star, an object made largely of deconfined quark matter. A further thought experiment plays out from there. If strange quark matter is the most stable form at high density, a small chunk, a strangelet, might in principle convert nearby nuclear matter into more strange matter. It sounds like a sci-fi chain reaction. In practice, there is no evidence for roaming strangelets turning matter inside out, and safety studies for high-energy experiments consider and rule out such scenarios. Still, the idea raises a real point. Stability is not a single hilltop. Under different pressures and conditions, matter may settle into different basins of stability that we cannot reach on Earth. Between neutron stars and black holes sits the proposal of quark stars. Compress a neutron star beyond its usual limits, and neutrons may dissolve into a sea of up, down, and strange quarks. The object would be more compact than a neutron star, but not collapsed into a black hole. Observations of very small radii, sudden changes in pulsar timing, or unusual cooling could hint at such stars. If confirmed, they would be entire celestial bodies sitting in a phase of matter we have only sketched in equations. From there, widen the map to what we do not yet know: dark matter. We infer dark matter from its gravity. It bends light, binds galaxies, and shapes large-scale structure, yet it does not shine or absorb like ordinary matter. If dark matter is made of particles, those particles could have their own forces and families. Some models imagine dark electromagnetism, with dark protons and dark electrons making dark atoms. If so, dark matter could build dark molecules, dark liquids, even dark crystals, phases of matter that sit beside our world but barely touch it. We would see them only indirectly, in small shifts in galaxy motions, in subtle patterns in the cosmic microwave background, or as rare signals in underground detectors. It is a reminder that phase of matter is not limited to what we can hold. It extends to whatever particles the universe offers, seen or unseen. Even within ordinary matter, our catalog grows whenever we push conditions. Supersolids blend lattice order with frictionless flow. Time crystals repeat in time at fixed rhythms under periodic driving. Topological insulators conduct on edges while their interiors stay quiet. None of these were on a classroom list decades ago. They emerged when cooling got colder, control got sharper, and materials were tuned with fields, light, and geometry. Matter is not just particles, it is relationships. Change the strength and sign of interactions, the symmetry of the environment, the level of disorder, or the dimensionality, and new patterns appear. This is why the phrase new phase does not always mean new element or new molecule. It often means the same ingredients cooperating in a new way. Think recipe instead of pantry. Temperature, pressure, and density matter, but so do symmetry, topology, and entanglement. Shift one, and the collective behavior can switch. A phase is a style of order, a way particles share information, move energy, and handle disturbances. Quantum computers push us toward corners where such styles may multiply. Qubits cooled near absolute zero and steered with lasers and microwaves occupy regimes where coherence, the alignment of phases across many particles, matters more than heat. Here, engineered lattices, synthetic gauge fields, and driven systems can show behaviors not seen before. Quantum simulators, well-controlled arrays of atoms, ions, or superconducting circuits let us dial interaction strengths and watch phase diagrams unfold. It is reasonable to expect surprises. Quantum liquids with new kinds of order, entangled lattices whose properties are defined by correlations rather than positions, or protected modes that live at edges and corners in higher-order topological phases. The history of physics is a history of such surprises. Superconductivity appeared in Mercury at low temperatures with zero resistance and expulsion of magnetic fields. Superfluidity showed that liquids can flow without friction. The quantum Hall effect revealed conductance in perfect plateaus. Each time, familiar particles in unfamiliar company did something new. Our lists changed because our questions changed and our tools improved. This leads to a quiet shift in how we define a phase. In the classical world of ice cubes and iron bars, we point to structure and measurable properties, density, compressibility, heat capacity, long-range order. In the quantum world, phases can hide in patterns of correlation, in how a system answers specific probes, or in numbers that count, winding in abstract spaces. You can have two samples that look similar under a simple microscope, yet one hosts edge states that refuse to backscatter and the other does not. The difference lives in the global organization of the quantum states. Quantum phase transitions underline this point. Unlike melting or boiling, These transitions occur at absolute zero and are driven by tuning a parameter such as magnetic field, pressure, or interaction strength. The system's ground state, the lowest energy arrangement, changes its character. No thermal jiggling pushes the switch. Quantum fluctuations do. At such a transition, what defines a phase is not where atoms sit, but how they are collectively organized by symmetry, entanglement, or topology. Some phases are symmetry protected. They are distinct only while certain symmetries are intact. Break the symmetry by adding a magnetic impurity, by tilting a field, or by altering the boundary, and the protected edge modes disappear and the distinction fades. The phase is real, yet conditional. This is not hand-waving. It is a precise statement about what patterns cannot be removed by smooth changes that respect the symmetry, and what patterns can be removed when the symmetry is broken. Measurement itself can matter. In some systems, phases are best told apart by how they respond to a twist, a boundary, or a timed sequence. Two samples may share the same spectrum of energies but differ in their response when you loop a parameter around in time. The identity of the phase is then tied to a protocol, not a snapshot. That sounds like philosophy, but it is testable. Prepare, drive, measure. The pattern either shows up or it does not. The quantum Zeno effect is a related oddity. In a simple picture, frequent measurement can freeze evolution. If you check a system often enough in the right way, you can pin it into its initial state and prevent transitions that would have happened in the dark. This is not about magic. It is about how measurement updates the state. In driven many-body settings, the watchfulness of a probe can change the effective dynamics, sometimes stabilizing patterns that would otherwise decay. Where phases depend on coherent motion, the act of probing can help or hinder, which means the boundary between the system and the observer is part of the setup. Entanglement goes one step further. In many-body systems, the web of entanglement, the pattern of shared quantum information between parts, can define the phase. Measures like entanglement, entropy, or the presence of long-range entanglement distinguish phases that are identical under ordinary local probes. Topological order, for example, cannot be detected by a simple order parameter like magnetization. It is revealed by ground state degeneracy, tied to the shape of the sample, by protected edge modes, or by how the system responds to a non-local twist. In such cases, a phase is a property of correlations of relationships, more than of individual particles. Seen this way, phase becomes context. It is the answer a system gives to a class of questions. Ask a different class of questions, and you may group states differently. This is not relativism, it is precision. We say a magnet and a paramagnet are different because one breaks spin rotation symmetry and the other does not. A different question would lump them together and split something else. In modern, condensed matter, phases are often indexed by invariants, numbers that do not change under allowed deformations. Those numbers are not written on atoms, they are written on the structure of the state space. This perspective does not erase the classical picture. Ice is still ice. Steel is still steel. It adds layers. A superconductor is not just a perfect conductor. It is a phase where electrons form pairs and move coherently, giving rise to quantized magnetic vortices and a gap in the spectrum. A topological insulator is not just an insulator with a messy surface. It is a bulk state with a non-trivial invariant that forces conducting edge modes. A time crystal is not motion without energy cost. It is a driven system with a stable subharmonic response, protected against small errors. It also affects how we search. To find new phases, we do not just look for new elements. We design new questions and new drives. We twist layers, pulse fields, add disorder, and confine motion to lines, sheets, and shells. We measure not only currents and voltages, but correlations and responses to loops in parameter space. We count plateaus, look for protected crossings, and track how interference patterns change under swaps and braids. The deeper message is steady. Matter is built from particles, but phases are built from patterns, interactions, symmetry, topology, and measurement. Knit those patterns together. As we push to extremes in temperature, density, purity, and control, we meet phases that were invisible before, not because the particles changed, but because the relationships did. This idea touches on the deeper philosophical debates around quantum mechanics. What is a state, really? Is it something that exists on its own, waiting to be found? Or something that takes shape when we measure it? Different views of quantum mechanics frame this differently. In the Copenhagen picture, a system does not have definite properties until a measurement is made. In the many worlds view, all outcomes exist in parallel branches, and measuring just selects one branch for us. Pilot wave theories keep definite particle paths guided by a hidden wave. They disagree on story, but agree on a fact that matters for physics. Observation is an interaction. Measurement is not a glance. It is a push and a pull. In some experiments, that push is part of what sets the phase we report. This matters when we talk about phases as contexts. In well-controlled platforms, optical lattices, ion traps, superconducting circuits, researchers can build artificial materials with knobs for interaction, strength, geometry, and noise. Change the probe you use, or entangle one part of the system with another, and the measured response can cross a threshold that marks a new phase under that mode of interrogation. That is not a trick. It is a reminder that the label we assign depends on the questions we ask and the symmetry and constraints we preserve while asking them. None of this means anything goes. Phases still obey rules. Superfluids still show flow without viscosity. Time crystal responses still lock to a subharmonic beat under periodic driving. Topological edges still conduct when the protecting symmetry is intact. The softer truth underneath is that matter can be both stable and conditional. Conditions: temperature, pressure, field, disorder, boundary, and probe decide which pattern wins. Quantum phase transitions show this cleanly. At absolute zero, with heat removed, a system's ground state can change character when a control parameter is tuned. No melting or boiling is involved. Instead, the organization of correlations and symmetries shifts. Two samples can look similar by ordinary structure, yet differ in the topology of their quantum states or in how entanglement spreads across them. Some of these symmetry-protected phases keep their identity only if a symmetry is respected. Break the symmetry, and the distinction dissolves. Measurement can even slow or steer evolution. The quantum Zeno effect shows that frequent checks can freeze a transition that would otherwise proceed. In certain driven, many-body systems, the way we probe sets the effective energy landscape. Again, not mysticism, just dynamics that include the measuring device within the description. Entanglement adds another layer. In many particle systems, the pattern of shared quantum information can define a phase even when local observables look the same. then a phase is a property of relationships, not of single particles. With that in mind, return to changes you can see. Phase transitions are not rare events. They are the daily work of matter. Add heat, and a solid's atoms vibrate more strongly until their fixed positions are no longer stable. The lattice gives way and a liquid forms. In a liquid, particles are still close, but they slide past each other and flow. Heat further, and particles gain enough energy to escape into a gas. Boiling is not only bubbles, it is a shift from packed neighbors to mostly empty space between collisions. Cool a gas and the process runs in reverse. Condensation slows molecules until they stick and pool as droplets. Cool a liquid and freezing locks particles back into an ordered array. These boundaries are not rigid walls. At the triple point, one exact set of pressure and temperature, solid, liquid, and gas, coexist. The balance is delicate and exact, showing that what phase am I can have a mixed answer when conditions sit on a knife edge. Some paths skip the middle. Sublimation turns a solid straight into a gas. Dry ice makes this obvious, but ordinary ice can do it slowly in a freezer, which is why food dries out over time. Deposition is the reverse. Water vapor in cold air lands on glass and forms frost without passing through a liquid film. We see slow transitions in materials that seem fixed. Rock deforms over long times under pressure. The mantle flows in slow convective currents. Glaciers, made of solid ice, creep down valleys. Metals expand with heat and contract with cold. Polymers and glasses relax internal stress and change stiffness with age and temperature. These are shifts in structure and motion that do not require boiling or melting to be real. Phase changes are not only about temperature. Pressure can rearrange atoms. Carbon under intense pressure forms diamond. Magnetic fields can flip a material from non-magnetic to magnetic order. Electric fields can turn an insulator into a better conductor. Light can drive changes in crystal structure or in how electrons pair. The map of phases is drawn in many variables, not just one. Biology uses similar logic. Cell membranes change from more rigid to more fluid as temperature rises or composition shifts. Proteins fold into shapes that can switch under pH or binding small threshold-like changes that act like phase transitions in function. In the brain, large groups of neurons shift between patterns of activity with abrupt onsets that resemble physical thresholds. These are not phases in the strict thermodynamic sense, but they show the same pattern. Parameters cross a boundary, a new mode appears, and behavior changes. Even the air around you is a gentle engine of transitions. Warm breath hits cold air and condenses into a visible mist. A mirror fogs after a shower when water vapor cools and becomes droplets. A lake feeds a morning haze as sunlight warms the surface, lifts molecules into the air, and then lets them condense higher up when they meet cooler layers. No drama is required, energy in and out, and phases respond. Step back to the quantum view for a final link. In a modern lab, the labels we apply superfluid, topological insulator, time crystal response depend on how a many-particle system organizes motion, stores phase information, and resists noise. Sometimes the telltale is a gap in the spectrum. Sometimes it is a protected edge mode. Sometimes it is a long-range coherence that keeps a rhythm under a periodic drive. In a few cases, the boundary between one phase and another is revealed only by a specific protocol, such as braiding excitations or looping a parameter and reading out the geometric phase. In that sense, phases are both objective and contextual. Objective because the same protocol produces the same signature. Contextual because the signature exists only for that class of questions. Across all of this, one thread holds. Matter is not static. It is a collection of patterns that appear, persist, and give way as conditions change. We used to sort those patterns into 3 bins. We now keep adding more because the world allows more when we cool further, squeeze harder, purify better, or drive just so. They are progress evidence that careful questions reach deeper and find new kinds of order. It is fair to ask what this says about us. The answer is modest. Our role is not to impose a story on nature, but to write down the rules the patterns seem to follow and to test them. Sometimes the pattern sits in positions and bonds. Sometimes it sits in correlations and topology. Sometimes it sits in time. Each case broadens the word phase, from a label on a chart to a way matter organizes motion and information. Change is the constant beneath these examples. Ice melts, water boils, rock flows in slow motion, plasmas braid along magnetic lines, superfluids keep moving when pushes stop. Time crystal responses tick at steady subharmonic beats. Quark matter may flow with tiny viscosity at extraordinary temperatures. A material's name does not fix its behavior. The environment and interactions do. If you look around a quiet room at night, the stillness feels complete. A lamp, a blanket, a glass of water, they seem at rest. Underneath that calm, atoms vibrate, molecules collide, and fields fluctuate. The air trades heat with your skin. The water in the glass evaporates molecule by molecule and condenses again on any cool surface. Your breath carries tiny droplets that appear and vanish as temperature and humidity change by small amounts. The room is not paused. It is busy and balanced. The lesson is practical and simple. Phases are not just categories. They are tools for thinking about how matter shares energy and information. They shift with temperature and pressure, but also with symmetry, topology, and measurement. They can be robust to noise when protected by a global invariant, or delicate when a key symmetry is broken. They can be simple to see or hidden until the right probe asks the right question. The list will grow. It will grow because laboratories can now cool to billionths of a degree, confine particles to sheets and lines, twist crystal layers by tiny angles, and drive systems with programmable sequences. It will grow because telescopes and detectors see matter under pressures and temperatures we cannot make on Earth. It will grow because models guide us toward corners of parameter space that were once unreachable. Each addition makes the map of what matter can be a little richer, and the link between phases and function a little clearer. You do not need to memorize the names to keep the point. Matter adapts. Under the right conditions, it becomes rigid, or fluid, or charged, or coherent, or ordered in spaces we cannot draw. It can hold multiple tendencies at once and switch when pushed. That flexibility is not a flaw. It is why the world works, from the way ice floats, to the way signals move in a chip, to the way stars form and fade. As the night settles and sounds grow soft, it is easy to imagine the world holding still, yet the physics we have traced says otherwise. Even the quiet things are busy. Even the simple things are layered. Even the familiar things have edges where new behavior begins. Rest comes not from stopping that motion, but from trusting that the motion follows rules we can learn and use. Let the room be calm. Let the atoms do their work. Let the phases change where they must and hold where they can. The universe will keep its slow, careful pace. and you can keep yours. Close to still, but never truly still, like matter itself, settling into balance as the day turns to night.